and perhaps you'll tell us more about what's next there, talking about Krylov subspace diagonalization and statistical failures.
So, okay, first, thanks a lot for having me here. My first time in Cambridge, so super happy to finally get to visit this city. So this is into the work that I did when I was at QKSD together with our colleagues at Chebyshev. And it's actually a brand new piece of work. So the paper is going to be out in the archive, I think, next week. And it's really the first time that I tell about this work. So you are the first people to ever hear about this. And so I'm excited to share, and I would love to hear your feedback. So it would be great to keep this talk interactive, ask me questions. That would be great for us to get your feedback on this. And yeah, so in this work, we are trying to compare two algorithms, the quantum Krylov subspace diagonalization and statistical phase estimation. So we are trying to build a framework in which these two algorithms can really be thoroughly compared to give some indications of like which one of the two should be used in the future. Okay, so really our goal is to compute molecular electronic ground state energies using quantum algorithms. And we are in the setting of early fault-tolerant quantum computing. So in a setting where we have some level of quantum error correction, so we can, afford kind of deep circuits, but not fully error-corrected devices. So we are still limited in the circuit depth and also in the speed of the quantum operations, so the number of repetitions that we can afford, and of course in the number of logical qubits. And so there are these two algorithms that were put forth as good potential quantum algorithms for this regime because they have these good trade-offs in the number of qubits they need, in the circuit depth, in the number of repetitions. But it was not clear to us which one we should use. So really the goal was to understand better, like if tomorrow we have a good quantum device, which one of the two would we choose? Okay, and it's nice because we can really compare these two algorithms because we can express both of them in terms of the same quantum primitives that are the expectation values of Chebyshev polynomials of the Hamiltonian. So basically, we can express the two algorithms as really obtaining these expectation values on a quantum computer for similar order of the Chebyshev polynomials. And then it's just a different way of classically processing the quantum signal. And this is nice because it can really be efficiently implemented in a quantum computer. We know how to do this. And so we have our molecular Hamiltonian and a block encoding of this Hamiltonian and this reflection operator. And the product of the reflection operator and the block encoding of the Hamiltonian is basically this walk operator. And if you repeat the walk operator, so k applications of this walk operator on the initial states on the system qubits and using some ancilla qubits for the block encoding, basically implements this expectation values of Chebyshev polynomials, which in practice can be really measured like this as preparing the states with k over 2, so it's like k over 2 times the walk operator, and then you measure the expectation values of the block encoding or the reflection operator, depending on if your K is odd or even. So this is very well defined. There are a lot of papers that discuss how to basically implement this block encoding depending on your Hamiltonian basis. So this is something we assume that we can do, that we have, and then we want to compare these two algorithms. So this is really a high-level description of how they work, and then I will go into detail afterwards. So for the quantum Krylov subspace diagonalization, so QKSD, what we do is that we prepare the Krylov quantum states, and then we measure the matrix elements of the H matrix and the overlap matrix on the quantum device. And finally, we have this generalized eigenvalue problem that we solved classically to get the approximate eigenstate and eigenenergies. And here, in this setting, the Krylov states that we use are the Chebyshev polynomials applied on the initial state. There can be other ways of doing that, but this is this. So you can also produce Krylov states by applying the monomials of the Hamiltonian, but in the setting we use here, it's Chebyshev polynomials, and it's also the most efficient implementation. For SPE, it's a bit different. We can use the expectation values of the Chebyshev polynomials to reconstruct this cumulative distribution function. I will show you how it's related. But basically, the goal is to construct this cumulative distribution function from quantum measurements. And then this basically relies on the probability distribution, and this is a Heaviside function. And so basically, it's a function that oscillates like this and then jumps whenever you are placed at an eigenstate or an eigenvalue, that the x will be in the eigenvalue space. And so when you have a jump, you can localize the eigenenergy. And so once you have an approximation of your cumulative distribution function, you just use a classical search procedure, and we can find your eigenenergy like this. Okay, so it was not so easy to compare these two algorithms because in the case of QKSD, the bounds that we know, so the bounds that allow us to basically choose the circuit depth, so the maximal Chebyshev order that we are going to use, and the number of measurements, they are known to be very, very loose. So if you just rely on the bounds, the bound would tell you to choose a circuit depth that's actually much worse than what you need. So that would be a bit unfair to compare, to use these bounds to compare QKSD and SPE. In the case of SPE, the bounds are known to be tight-ish. But the definition of SPE in terms of Chebyshev polynomials was not known yet. So this is it's part of this work to really express SPE in terms of expectation values of Chebyshev polynomials, so it can be really compared to QKSD. And so yeah, because we don't want to rely on the bounds, we are actually going to emulate the algorithms. So we are going to really introduce some approximations such that we can classically emulate the algorithms. And the way we do this is we're not implementing the quantum circuits, we're just approximating these expectation values classically. And for this, we use two approximations. So we basically introduce this resolution of identity here in the expectation value. And these are the eigenstates of the Hamiltonian, the full n eigenstates of the Hamiltonian. And so the first approximation that we do is that we don't use the full n eigenstates of the Hamiltonians because there are exponentially many, but we use a subset of them, like the first R eigenstates. And then this can be just rewritten like this, where this is the overlap of the eigenstate R with the initial states. And so, of course, we don't have access for most of the molecules of interest. We don't have access to the true eigenstates, but just approximated eigenstates. We can just approximate them with some classical methods. In this work, we use DMRG. So we have a set of approximated eigenstates, and we just use those to get the expectation values of the Chebyshev polynomials at order k. And then once we have those, we can just use either QKSD or SPE to reconstruct, to post-process at this moment, and then find the ground state energy. And so that's very convenient because now we have really the same expectation values constructed in the same way for both algorithms. And really, the only thing that changes is how we post-process them. Okay, I will tell you a bit about the type of systems that we looked at and how we really expressed our Hamiltonians. So we looked at these four molecules that you recognize they are used often for quantum computing because they're quite a strong electronic correlation, and the active space sizes start to be large enough that it's hard classically to simulate them. So we took naphthalene also as just as a reference where we could actually calculate the first 500 eigenstates using full CI, so the exact first 500 eigenstates of this. So we, this is at least we have the exact eigenstates. There's not so much an approximation as for those, but for those we calculated the first 40 eigenstates using the NRG with a bond dimension of 1000, which, it's not clearly not enough to describe these systems well, but that's also the limitation of the classical algorithms. So clearly our eigenstates are not, or at least the eigenenergies are not in chemical accuracy with the true ones, but we decided to use that and assume that this is a good enough representation of the eigenspectrum. And then we use, so here, in this case, we just use the R3 Fock state as an initial state because it has good enough overlap with the ground state. In these cases, the R3 Fock state has a very bad overlap with the ground state, and usually people start with a superposition of state determinants, like an MPS or something like this. So what we did was to just express the initial states as a superposition of the eigenstates. We'll just basically we fix P0, and then we have an exponential decay over the next eigenstates, and that produces an initial state energy error that's on the order of 10 to 100 millihartry, which is a reasonable starting point. Okay, and so the next few slides, they're really for context, just to explain how we implement our Hamiltonians, like the form of the Hamiltonians that we use. So you recognize this. This is the molecular Hamiltonian with the one body term and the two body term. And so this is the physical Hamiltonian. And as you know, in order to block encode the Hamiltonian, we need to shift it and rescale, normalize it such that the norm of the Hamiltonian is bounded by 1. Otherwise, you cannot block encode this, and you cannot use Chebyshev polynomials either, because Chebyshev polynomials are also only defined between -1 and 1. So you really need to do this, and depending on how you do this, that really affects the cost of these algorithms. Similarly, as in quantum phase estimation, the cost of quantum Krylov and SGD depends linearly on lambda. So it's important to choose a representation of your Hamiltonian that gives you a good normalization factor. If you do like naive approaches, you might have a very bad lambda, and then the norm is really, really below 1. And so then it just takes you a lot more effort to run these algorithms. So what we use is this really state-of-the-art technique that's called THC Bliss. And I want to tell you about this because I think it's really cool. It works well. It's not very important for what follows, maybe a bit somewhat, but I want to just tell you, give you a few slides about this, just because it's a cool technique, and I go a bit fast, and if you have questions on this, at least there's slides. Okay, so to factorize the molecular Hamiltonian, what we usually do is to re-express the two-body term as a product of single particle excitation operators like these. When you do this, because of the fermionic commutation relation, you just have to modify the one-body tensor like this. And then once you have this, you can re-express the two-body tensor in this factorized way, where the sum here goes over m. M is the THC rank, and the THC rank it grows linearly with the number of orbitals. It's something like 5 times the number of orbitals, like 7 times the number of orbitals, depending on the system. And so you go from a tensor that was n to the 4 to something that has n to the 2 terms. It's a compressed representation of your Hamiltonian. These are normalized vectors. These are just scalars, and these normalized vectors, they can be embedded in a unitary transformation. So you can represent the action of the vectors on the fermionic operators through a unitary operation that can just be, it's just basically a rotation of the orbitals. So it can be implemented easily with a product of Gibbons rotation on the quantum computer. So then, when you use this form, the Hamiltonian looks like this. So you have your zeta, the zeta tensor that multiplies into these operators. These are the Gibbons products of Gibbons rotation that I just told you about, and these now are just diagonal operators. You just Jordan linear them, and then you have this final form of your Hamiltonian that's pretty easy because we now have the only z Pauli operators. You just have to implement these unitaries and then the z Pauli operators, and then this is the corresponding norm and shifts. Okay, so this was THC, and now Bliss is so the block invariant symmetry shift. What it does is that instead of working with the system Hamiltonian, we work with the modified Hamiltonian, this new H that basically we subtract these operators from the Hamiltonian. So this is the particle number operator. This is the product of the Hermitian one-body operator and the particle number operator, and this is the number of particles. And we have the three parameters, like the alphas and the full beta matrix, that you can optimize in order to minimize the norm. And really, how this works is that it's going to shift all the symmetry sectors of your Hamiltonian that you are not interested in. So you are going to modify the eigenspectrum of the other symmetry sectors of the Hamiltonian, so the ones that don't have the number of particles that you're interested in. You modify, you can compress them such that you can lower the norm of your Hamiltonian. The only symmetry sector that is going to remain invariant is the one you're interested in. So it doesn't change the eigenvalues that you're looking for, it just changes the eigenvalues outside of this symmetry sector, and thanks to this, we can really lower the one norm. And so it's very easily done. So they're basically the new 1 and 2 body tensors that are basically redefined like this in terms of the alphas and the betas. And then you can just use THC on those and optimize the coefficients here to lower your norm. And just as an example, for these iron sulfur clusters, this is the norm if you just do the naive Pauli decomposition of your Hamiltonian. So it would be around 137 and 417. This is if you just do THC, so 105, 294. And if you use THC bliss, you go down to 24 and 63, which is much better. So this is what we use for our estimates in this paper. It's really kind of the best one can do at the moment. All right, so now I want to kind of deep dive in the quantum Krylov algorithm, the theory and the performance of the algorithm. Okay, so as I said, we work in this Krylov basis, so where we apply the Chebyshev polynomials to an initial state, and that creates our Krylov vectors. And then it's very easy. Then we know these relationships between the products of Chebyshev polynomials. Also know that H is Chebyshev polynomial of order 1. So then you can just simply re-express these matrix elements as the sum of expectation values of Chebyshev polynomials. So this is very easy, and K here is the size of our Krylov space, and it will define the accuracy of the algorithm. So the larger the space, the better the accuracy. Of course, if you use K being the size of the Hilbert space, then this is exact. But it's also not useful. And the nice thing is that you might think, looking at this, that this algorithm scales with K squared, but it has a nice deep matrices. They have a nice property that they're couplets. So you actually only have to measure 2K minus 1 expectation values to fully know H and S. So it's this, basically the algorithm scales linearly with K. And we also know that in theory, there is an exponential convergence of the energy error with K. So when you increase K, the energy converges exponentially. Okay, and in practice, it's a little bit more complicated because this is a generalized eigenvalue problem. So of course, if there is any numerical issue, or if S is ill-conditioned, then you have problems when you invert S and when you solve this. So there should be some careful reconditioning of the overlap matrix. And also, this is only in the ideal case that you have access to the exact Chebyshev expectation values. But in our setting in a quantum computer, you will have shot noise, and this adds an extra layer of complexity. that's already discussed now. Okay, but first, next two slides, they are only exact simulations, so we don't add noise on the expectation values, they are just the exact expectation values. Okay, here what I show is the convergence. So this is the energy error, and this is K, the size of the Krylov space. And this is done for different representation of the Hamiltonian. So I told you about THC bliss, but here we use different representations. THC, also double factorization, the naive Pauli representation, and the synthetic that I will tell you later what this is. And you see that the norm really affects, so all the methods, they produce different norms that are given here. And you see that indeed THC bliss gives you the best convergence with K, because it has this smaller norm. There's another thing that really plays a role here is where the eigenvalues lie in the spectrum. So now your spectrum is normalized, it's between -1 and 1. And the Chebyshev polynomials, they oscillate faster close to the edge of the spectrum. So you see these plateaus, they arise because you add an extra Krylov vector, and it's just linearly dependent with the previous ones. So when you have your overlap matrix and you diagonalize it to invert it, what you have to do is regularize it. So you throw away all the eigenvalues that are smaller of a certain threshold. Here we took 10 to the -8. But of course, if you add a Krylov vector that's just linearly dependent with the other ones, it just adds another like 0 eigenvalues. You throw it away, and so your space remains the same, and you cannot go down in energy. So it's a bit annoying because in a setting where you don't know your ground state energy, how do you check convergence? Because it could be here, and you want to, or even here, and you add more, you increase K on your quantum computer, and you think, okay, maybe I reached convergence in my energy, but actually you just didn't go far enough. So it's a bit of a problem, these plateaus in a practical setting. And you see that this synthetic Hamiltonian has a larger norm than THC, but we engineered the shift such that the ground state energy is really close to -1. So the Chebyshev polynomials, they oscillate very fast there. So you see that there we don't have this issue, and it converges super well. So now we kind of know how to go to this regime, and that would be probably what needs to be done next, is to use this SOSA Hamiltonian, so the sum of square Hamiltonians that basically really do that. They shift the spectrum close to -1, and then you can be in this case where you don't have such bad plateaus. Okay, what else did I want to say? I guess that's it. Okay, so when we saw this, we also thought here we take the Chebyshev, the Krylov vectors, they're spaced by 1. So we take Chebyshev over 1, 2, 3, 4, up to K. But we thought, okay, now we're adding the vectors that don't add more information. So why don't we just take larger steps? So this is what we tried. That sounds naively like a good idea. It's a very bad idea, actually. But I'll show you these results anyways. So now, instead of having a Krylov space size of order K, we take a delta K that's larger than 1. And so basically now we have this K prime. And so here, for example, for THC, the blue, so you can see where the blue is for delta K1. It converges a bit faster, but for a very large delta K, if we are here with just 2 expectation values, I can get the same energy as with basically 500 expectation values. So, and it's the same with THC. This is what we see. Principally, if you really undersample you're going to take you a lot more time to go down, but if you choose a good trade-off, then you can reduce the number of expectation values that you need to measure. And in principle, that should be better because then it means less measurement on the quantum computer and so improvement in runtime. So actually, doing this does not decrease the number of measurements. When you add shot noise, it's actually much worse to do this than using the delta K one. And this is,
Can you explain the seal there? Sorry, I'm going to repeat about this.
so the delta K.
Yeah, that's K.
Okay, so before we took Chebyshev polynomials that were really spaced by one. So really we take 1, 2, 3. And now we take, instead, like here, we just took Chebyshev order 294 and then 294 times 2. So it's really like delta K times, it's the definition.
Space.
Exactly. It's just like subsampling. So it's a subspace of your original problem, which we thought was a good idea since a lot of these matrix elements, they just create linearly dependent vector. They have splatters. So as you see, you can get rid of splatters. But when you add shot noise, then there is it's a different story. It's actually much worse to subsample. Much better to sample the full space. Okay, so what we did to show this, so here in this plot we see the number of measurements and the K. Okay, I need to explain a bit how to code. Here is the corresponding absolute energy error with K. So what we do is that we add Gaussian noise to all the expectation values. Just add the Gaussian noise with a standard deviation defined like this. And the measurement is actually divided between the Chebyshev polynomials in the best way, because what we did was to get this gradient vectors, the gradient of how the ground state energy deviates with respect to a change in each of these expectation values. We just did this with JAX. With the automatic differentiation, we got these graded vectors, and that's how we assigned the number of measurements. So basically, we fix the total number of measurements. We say, okay, we allow 10,000 measurements, and then we assign each of them. We assign a subset of these measurements to each of the expectation values according to this gradient vector. And so then this is stochastic. So we basically calculate the corresponding energy at a given K for a given number of measurements 100 times. This gives us an average error. And we look for the number of measurements such that this average error is below 1 milliampere with respect to the noiseless value. So this is the number of measurements that I report here. And okay, the S matrix needs to be regularized. Of course, you cannot, now you have noise, so you cannot just regularize with a small threshold as I was doing before with 10 to the minus 8, because the noise level is much higher than this. So you have to keep only the first few eigenvalues, because if you add another one that's just completely noisy, you just end up with a crazy energy. So you really have to keep the eigenvalues that are above the noise level. And that's really why it's better to use sampling of delta K, because actually, so this here shows the magnitude of the S eigenvalues. So this is the blue is the first, the second, and the third eigenvalue of the S matrix. And this is for, so if you look at the first one, this is for delta K equals 1, it's much larger. And this is expected, right? Because if you diagonalize the subspace of a matrix, the eigenvalues need to be lower than the full space. So the more you go in the scarce sampling, the smaller are the eigenvalues. And so the less tolerant is the algorithm on the noise. And this is really what we see now here. See that for if you keep the first, well, I guess if you keep the first eigenvalue or not in chemical accuracy, but if you keep the 3 first eigenvalues, you need for a K of 1000, you need less than 10 to the 6 shots, whereas if you are subsampling, you need like more closer to 10 to the 10 shots. So it's actually a huge difference. Yeah, and I mean, in our paper, we also have a full discussion, a full study of really the evolution of the S matrix with K. It's much more, it's better explained in the paper. But what we see is that the off-diagonal elements of the S matrix, they basically oscillate, but they don't grow with K. They are bounded. And the diagonal elements, they grow linearly with K. So this is really what we see here. So this is so it's interesting because if you use a small K, you can be so here, for example, if I'm at K 200, meaning a very small circuit depth, I am in chemical accuracy, but then I need 10 to the 14 shots. Whereas if I go to 1000, then my tolerance to noise is much greater, and I can then I need only 10 to the 5, 10 to the 6 shots. Okay, so this is all I wanted to say about quantum Krylov. At the end, I will really show basically this kind of plots, but together with statistical phase estimation, such that you see really which one works best.
So just for that, is the reason why you need less shots for a larger Krylov space is because of the condition of the S matrix?
Yeah.
Okay.
Yeah. Well, not the condition of the S matrix, but because really the eigenvalues of the S matrix, they are all going to grow, and also all going to space. So like the space between two eigenvalues are going to also grow linearly with K. Mm-hmm. So basically, you can resolve the eigenvalues from the noise level easier with less shots. Yeah. Okay. So now statistical phase estimation works in a different manner. As I said in the beginning, you have this probability distribution function, and what you need to build is this cumulative distribution function like this. So it's just the sum of the probabilities, or you can also re-express it like this with the Heaviside function. And then once you have this, it's a classical search algorithm that basically finds X that satisfies this condition where this eta is a lower bound on the ground state overlap. Once you have this condition, you find X, this is your ground state energy. But the problem is that we don't have this. We don't have this cumulative distribution function. We need to approximate it. We also don't know how to implement a Heaviside function on a quantum computer in principle. So we have to approximate this Heaviside function. Okay, and so yeah, in this paper, there was a very elegant way that was defined to approximate this Heaviside function with this other function, which basically use an expansion of the scaled error function, and then this gives you this expression here. These f's, they are well-defined scalars that are defined in this paper. So we use this form, and then once you use this in the approximate cumulative distribution function, you end up with a form like this. with these expectation values, these, all these coefficients, you know them, so you have to measure this, and then you have your cumulative distribution. And then once you have this, you can find the eigen. Okay, and as you see here, these are time propagator, not Chebyshev polynomials. And so SP is nice because in principle, it's Heisenberg limited, so it scales with 1 over the precision that you want. However, if this is expressed, if this is implemented with Frotter, the Heisenberg scaling is lost. So in this paper, in the paper that defines this cumulative distribution function, they proposed to sample this from a Taylor expansion of the time propagators. And okay, so it works well, but you do have a finite probability of sampling an infinite circuit depth. So not great, but it's not too bad because this probability of sampling an infinite circuit depth is exponentially small, but it still exists. But so we wanted to do 2 things: get rid of the issues and have an expression in terms of Chebyshev polynomial expectation values so that we can really compare to QKSD. So this is what we did. We basically re-expressed the probability distribution in terms of the arc cosine of the eigenvalues. And then I go a bit fast here, but basically you can look at the this distribution function with respect to minus the arc cosine or plus the arc cosine. You also know that the arc cosine is always positive. So if you leverage this, you can actually express, you have these 2 expressions for the plus and the minus is with a plus here. Then if you sum them, you get rid of these oscillating terms, and you can just express your approximate cumulative distribution function in terms of Chebyshev polynomials. And the sum here also goes up to 2k plus 1, so very similar as quantum Krylov, linear in k, actually, this is 2k. So really the 2 algorithms, they are going for a given k, they need 2k expectation values of Chebyshev polynomials and then post-process. So very, very similar circuit depth. K gives you the approximation. It's the approximation of the cumulative distribution function depends on k. So for a given precision, you need k. The way k and the precision is related was also defined in this paper. To understand this, you need to understand how this Heaviside function is approximated. But basically, the story is it uses this Fourier expansion of the scalar function. But the story is that the precision here that is given by the difference between the scalar function and this approximate function is overbounded by this term. And there is this term here that sums over an infinite number of Bessel functions. Not great to know how to calculate this in practice, but this is what we would like to do, because if you know this, then you can isolate k, and you have k in function of your precision. So then, for a given precision, you can just select the k that you did. So in this paper, they gave basically a bound on this bound, because they did not know how to express this sum. So they put this bound on the bound, and then from this expression, you can know k as a function of the precision. So what we did actually also in this paper was to, instead of bounding this bound, just calculate this bound. Actually, we show that using some easy formulas, we can actually really calculate this term. So this is basically the result. And here we show on this plot for this. This was the previous bound, this is the exact error, and this is the new bound that we calculate now.
And how did you get the exact error here?
So the exact value?
Yeah.
Yeah, so here it's really, so it's not in the Hilbert space. This is really in the, it's a function that goes between -1 and 1. You can really calculate it. Yeah, once you have the expression. So like this is numerical, and this is really from the bounds. And so for this cobalt molecule, we showed, so this is the previous bound, this is the new bound, and so this is the actual error that you get out of SPE. So basically you have the bound, this gives you K, and then you do SPE, the search algorithm. It can be better than this, but you never know. But for some points, it's very close to the bound, actually. So it means that it's a good choice of K to begin with. Okay, last slide. And this is basically the most important slide. It's really comparing the two methods. So, okay, this is what we did. So we ran QKSD for the different molecules, and we kept in the the S matrix, we kept the first 3 eigenvalues or the first 2 eigenvalues. This gives us a noise-free energy. And then we look for the number of measurements that we need, as before, to stay in 1 milliarc accuracy with this noise-free energy. So then we report at each K the number of measurements that we need. So here, for example, this is for iron 4 sulfur 4. The noise-free energy is this, almost 10 to the -3 R3. So almost, so in chemical accuracy, below 1 milliarc. And so it means that for this value of K, these are all the values for the last dots, the last markers for the group, the largest K value. So it means that, okay, for 1,000, yeah, for the 4,000 K 4,000, we need 10 to the 5 shots to get this accuracy. Okay, and then using this accuracy as the target for SPE, we estimated K needed for SPE and the number of measurements. The number of measurements in SPE depends on your ground state, the initial state overlap with the ground state, and it depends logarithmically on the precision. So this is why the number of measurements here is very low. But you see that now to have this precision, we are actually here in the circuit depth for SPE. So again, this is a bound. So the resulting SPE energy is a bit better. But for example, these two, they have the same resulting energy, and Krylov is here, and the SPE is the blue marker here. So for similar energies, you have, you can choose, like this is a bit more measurements. This is slightly deeper circuit. It goes down like this and up. So for the system goes down and up. This is expected because at one point, if you decrease too much the number of measurements, you have less than 1 measurement per K, and you start to be in this subsampling regime that I said is worse than sampling all the Ks. So this is then why it gets up again.
And here the M is the total number of measurements.
Total number of measurements across all Chebyshev measurements. So, I mean, I guess it's not so easy for QKSD, like in a practical setting. Because SPE has much better bounds, like the bounds are better defined, so it's easier to just select the circuit depth that you need and the number of measurements that you need. For quantum Krylov, you kind of need to check convergence. Like if I would have to run it tomorrow, I would probably have a guess K, very few measurements per Chebyshev polynomials, and then increase K until I see convergence. But as I said, not super easy because of the plateaus. So this is a bit of an inconvenience of QKSD, but it seems to lead to shorter circuit depth than SPE, and it can be competitive in the number of measurements. And SPE, okay, so I would say easier to choose your algorithm parameters, but larger circuit depth. Okay, so the takeaways from this talk is that we emulated these two algorithms for several molecules using this the approximated electronic spectra. We expressed the Hamiltonian with THC bliss such that the norm is as good as possible, and so the runtimes are as good as possible. SPE can be expressed. So we express SPE in terms of Chebyshev polynomials expectation values, such that we can really have a direct comparison with QKSD. We improved the bounds, the SPE bounds, to choose the K value by about 1.5. We showed that increasing the Chebyshev order step size can be harmful in a noisy setting. We showed that QKSD can be competitive to SPE in terms of shots. And at the end, for the systems we studied here, QKSD requires a shorter depth than SPE for a fixed accuracy. Okay, so thanks a lot for listening, and these are the people I work with on this paper, so Maru and Christian from Covestro, and also Stefan from Leiden University. Thanks a lot for your attention.
Yes. So the last point that you said where the circuit depth was less for the Krylov method, is that like your cool method depth of all of the circuits?
Yeah, that's okay.
Yeah.
So K is, so this is the maximal Chebyshev order you need.
Yeah.
So the depth of your circuit is going to be 2K.
Yeah.
Yeah.
So that
For both the methods.
Yeah.
So it means that the maximal circuit depth you need is 2K, so 2K repetitions of the warp operator.
Then if you were to implement it, but so Krylov is obviously taking overlap measurements.
It's really the same expectation values. That's the point.
Okay.
In both cases, what you need from your quantum computer is the expectation value of the Chebyshev polynomial. It really in both cases. And then this tells you what's the maximal order of this Chebyshev polynomial you need for a fixed accuracy.
So we can do it with a Hadamard test?
No, it's, yeah. I don't have the circuits here, but I can also point you to the paper that has the circuits, but it's like this. So it's you prepare, you apply W, K divided by 2 times. If it's odd, you measure the expectation value of the block encoding operator. And if it's even, you measure the expectation value of the reflection operator. That gives you exactly this. So you don't need an Hadamard test. You just need to prepare this. And for R, okay, so this is pretty straightforward on how to measure the expectation value, but for U, then you need to measure each term in the block encoding.
Okay, I see.
Hmm.
You can just do how they get to
Yeah, exactly. And because you have the select, you need to post-process your measurements because, yeah, you need also your ancilla qubits to be in the right, the right index, basically.
Yeah.
Thank you.
So it's not very efficient to measure this. But we had a previous paper with the Chebyshev guys where we showed how to also lower the cost of measuring this expectation values. Again. Yeah.
Thanks, Yusuf. With the QKSD algorithm, you showed the plot with the synthetic data. How exactly do you apply that shift, the shift of the?
Yes. Okay. So in our case, since we had the eigenvalues, it's like having a diagonal Hamiltonian. So we just shift and rescale the eigenvalues.
So
Oh, you have the terms of your Hamiltonian, and you just divide. Yeah, shift and divide. Yeah.
About that measurement. So if you measure the LCD state or in block encoding, won't you get the spread overlap or the spread of that value instead of?
Yeah. No. Okay. Yes. But so here the U you need to re-express. It's like if you have Pauli X you want to measure, then you measure the Adamant, right? You don't put the X, you put the Adamant gates, and then measure in the Z basis, and then so you would do the same here. Yeah. Yeah, it's true. You have to modify the U such that you don't get the square, but you just rotate to the Z basis, and then you can do the expectation value.
So in your final slide, you were showing subspace expansions with F1, S2, and then 3. So is that you only use the first 3 like singular values of K?
Yeah.
Did you look up further ones and they performed worse, or?
We did not, because in all the systems with the 3 eigenvalues were already chemical accuracy. So we didn't for more. But if we would have, we would have needed a lot more measurements. Yeah. Or a lot larger case. Yeah.
Let's confirm it again. You're sufficient.
It's still like this is